All right, so the goal today is to look at series parallel circuits, and let's get a color that we like. How's about red? Oh, I like this color. Series parallel combined circuits. And to start, we'll draw an example of one. So let's say we have, I don't know, a 2 ohm resistor here. And then in line with that, we have a parallel section. I think this is a little different than the one I drew yesterday. But we should be able to deal with it no problem. We'll put 6 volts here. Okay, so the way that we're going to solve one like this is we're going to look at this as having essentially 2 sections to it. Okay, so one section has 2 resistors in parallel. Okay, and then in series with that, we have a 2 ohm resistor. So if we think about what the current is going to do here, so actually put the positive side here. So interestingly, it doesn't matter which way we look at this. So what we'll have is we'll have a bit of the current traveling through each of these branches. Which do you think will have more current traveling through it? You think the 3 ohms, and that kind of makes sense, right? It's got a lower resistance and therefore should allow more current to travel through it. What do we know about the 3 and 4 ohm resistance in relation to what voltage will be across them? It'll be the same, right? Will it be 6 volts though? Why won't it be 6 volts, do you think? I'm giving you a hint by doing this. Right, because there's a voltage drop across this 2 ohm resistor, right? And whatever is left over after this voltage drop will be the equal voltage drop across each of these. Okay? So then, as our current passes through, it rejoins, passes through the 2 ohm, and comes to the ground. So step 1 in solving something like this is to solve for that branch that's in parallel. There's my parallel symbol. Okay. So if you remember our little formula for the total resistance in parallel, this little section, just calculate that. I get 1.7. Okay, that's supposed to be an ohm signal. So then, what I prefer to do is I like to, at this point, just redraw the circuit. It may or may not be necessary for you to do this. It's totally up to you. But I find as long as you keep track of everything in this way, it's really hard to make a big mistake. Okay? And then the next step is to realize now essentially we have a 1.7 ohm resistor in series with the 2 ohm resistor over here. So 1.7 ohms for this section and 2 ohms for this section. Okay? So if we draw the final sort of iteration of this, we should end up with 3.7 ohm overall resistance. Okay? So now what we have to do is we have to sort of figure out the current through this whole system here. I feel like I'm going to run out of room. I have to try to use a different program to be able to extend my page, which Brad told me about, but I'll look at that on another day. Okay, and so just so I have this in my back pocket to look at as I'm writing formulas so I don't have to memorize them, the first thing we probably want to do is we want to find the current in the entire system. So I should be equal to voltage divided by R. So we've got a 6 volt potential across this equivalent resistance. Okay, and it's 3.7 ohms. We'd expect about 1.6 amps to be traveling through this entire system. Okay, so I'm going to run out of room here. I'm wondering what the best way to do this is. I think if I add a layer, I can just pop. Oh yeah, good. So I have a little bit of room. Okay, thanks. Perfect. Okay, so what does that 1.6 actually tell us? It says what's leaving and what's returning. Okay, some portion of 1.6 goes through this, some portion of 1.6 goes through this, but all of 1.6 has to go through this. Okay, so what we'll do now is we'll use that concept of 1.6 amps traveling through this 2 ohm resistor to figure out the voltage drop on it, right? We know the voltage drop here, and we realize that that voltage, that 6 subtract that voltage drop should be the voltage drop over here, right? We have a total voltage drop of 6 across the entire circuit, okay? So whatever drops across here, subtract that away from 6, that's the remainder that's going to be across both of these together, okay? Do you follow that? All right, so let's find the voltage drop on the 2 ohm resistor, and that's just going to be IR, which in this case, it gets all 1.6 amps, and it's got a 2. So we should get, I believe, 3.2 volts there. A drop of 3.2 volts. Okay. So to find the voltage drop across the 3 and the 4 ohm resistors, we should just be able to take the total voltage, 6 volts, subtract that away, and that should be equal to 2.8 volts. No, oh yeah, sorry. 2. Okay, do you agree with that? Does that seem right? So 2.8 plus 3.2 should add up to 6. Now we can look at the 3 and the 4 ohm, and we can find the current through each of them. So I3 should be equal to V over its resistance. So it's got a voltage drop of 2.8 volts across it, as will the 4 ohm, because they're in parallel together. Okay, divided by 3 ohms. Three. Do that right? Yeah, I think so. Okay, 2.8 volts there. Oops, for 4 ohms. 0.7 amps. Okay, so 0.7 amps travels through the 4 ohm resistor, and we expected it would have a little bit less. Now what should 0.93 and 0.7 add up to being? And so they should be pretty darn close to 1.6, and if we just do to one significant figure, that's exactly what you get. Okay? So there is the method of solving a mixed parallel and series circuit. Do you want to try another example? A little more tricky. Okay, let's do that then. Did everyone have a chance to write that down? Perfect. Oops. try one in blue. So what we want to know is, again, just to solve, so the type of question you'll be asked is solve for voltage drop and current through each resistor. And with just like the simple sort of reductive method that we did there, we can make this work. Just realize I can make this draw straight lines for this. Oh, that's handy. Okay, we'll call this, I don't know, let's make something up. 2 ohm. We make it really tricky. Oops. It's not very straight. There. I know. Okay. This at first glance maybe looks a little bit tougher. Should we add one more? Let's add one more. Make it actually tougher, because otherwise it's pretty much the same one we just did, more or less. 1, 2, 3, how about 4? Perfect. Okay. Maybe I won't completely do all of this, but what we'll do for sure is we'll reduce it down, and then we'll start to work back out of it, okay? So what do you guys think is the first step that we want to do? Yes, so find the equivalent resistance of this, okay? Then if we look, this resistance is going to be in series with this 2 ohm resistor here, which will then be in parallel with the 1 ohm, okay? So let's start with step 1 here. Let's find the R of the parallel section there. What's that? Is it? Oh, well, that's handy. Okay. And, oh, am I going to really want to redraw this every time with all those straight lines? It looks so nice. Or not. Uh-oh. That is just not very pretty. You guys don't really care if it's straight line, do you? Good, because it's much faster to not do it with a straight line. Okay? So if you want to call this like A, B, that helps you keep track. C we would reduce to this. This. Okay, we got to figure out this parallel section, and we should be done reducing the circuit to its equivalent resistance. It's 0.78 for here. So from the perspective, I guess, of the source of the voltage, you're going to experience equivalent resistance of 0.78 ohms overall. Yeah, let's put a 6-volt on there. So a pretty complicated circuit actually just comes down to, at the end of the day, a a fairly simple little model of the circuit. Are you guys following along with this? Does this make sense to you? Okay, so, I used my whole page. I didn't use up here though. That wasn't very well done. Too bad. Will you have to do this method? Yes, you may have to do this method, especially if it's a complicated circuit. They can come much more complicated than this. I mean, we can put parallels and whatever we want, like everywhere, and sometimes, yeah, you have to do 3 or 4, maybe 5 drawings till you break it down to its simplest form, and then you have to slowly build back, right, and see what one drawing leads you to in terms of how to solve these on the way back up. So I'm just wondering if there's a select tool here. There is. I wonder if I grab all this and I copy it, and then I slap another layer on. Maybe this isn't the most okay. Now can I? Yes, sweet. Except, how do I? Does it stay like that the whole time, or? Okay. Okay. Well, that's not bad. That's not a bad deal. That kind of worked. Okay, so let's start figuring some stuff out. So let's find the. Ooh, nice color. Let's find the total current in this system. So how do I solve for current again? Voltage over total resistance, so 6 volts, 0.78 ohms. The total current of 7.6 amps. Okay. Is there anything on here that gets the full 7.6 amps? Not really, right? Because if we look, you got some current busting off that way, some coming through here, some going there, and some going there. It's not quite as easy as the last one, right? Where all the current will go through one branch. So this may or may not be useful. However, if I look here, okay, what I can see is this is essentially, you know, the same as having these 2 resistors in parallel. And if I know there's 6 volts here, there must be a 6 volt drop here, okay? And there must be a 6 volt drop here, and that's going to be useful for us. Okay, and we'll see why in a second. All right, so you have to be a bit of a detective here. You have to sort of look at what you're given and work your way back. I don't know if there's like an exact, you know, method for doing this. This is kind of my way, and you got to be a bit of a detective. Okay, so we know there's a 6 volt drop there. So what I'm thinking is, if we know there's a 6 volt drop there, we should be able to work out what the current through this one is, which I think shouldn't be that hard to sort out. And then realizing that there's a total of 7.6, but some goes here, understand that the rest must continue along this branch, right? Then we can figure out this one, right? And we can figure out the voltage drop here. Then we should be able to figure out the voltage drop here and solve out the rest of the problem. So it's a bit of work. Got to go kind of at her slowly, but let's go with that. Okay, so let's figure out the current through the 1 ohm resistor. So we see there's a 6 volt drop over it, and it's a 1 ohm resistor, and so you should have 6 amps going through that guy right there. Does that make sense? We'll even just draw it in here. So 6 of all of our amps go that way. So how much of our amperage continues this way then? So we have 7.6 total. 6 of them go there. Right. We got to have 1.6 left over to travel through the rest of the circuit. Does that make sense why that would happen? The resistance here we can see even just by the 2 ohm resistor, right, is higher than 1 ohm. So that makes sense, right? There's going to be more current going where there's less resistance. Okay? So if we know there's 1.6 amp going down this branch, there has to be 1.6 amp going through this resistor. So the second thing we'll figure out is the voltage drop across the 2 ohm resistor. V equals IR. Current is 1.6 amps. Resistor we have there is a 2 ohm. So we should have 3.2 volts dropping there. Okay? Let's just take it back a step and just recall what we can do with that now. Oops, what just happened? Not like that. What is this thing? Okay. I was trying to change my pen color. Okay, so we had 6 volt drop there. So then we have a 6 volt drop across all the rest of this. Okay? All the rest of this gets a 6 volt drop. Okay? However, we just figured out that of the 6 volt drop that goes on this branch, and this is going all the way back to here, right? 6 volt drop there, 6 volt drop there, 6 volt drop there, and of the 6 volts, 3.2 is lost here. So how much is left for over here? 2.8. So we can then write in, we've got a 2.8 volt drop there. Since these are in parallel, we must have a 2.8 volt drop here as well. Okay? And the rest should be somewhat easy to sort out. And we figured out this was a 3.2 volt drop up here. So let's continue. So we have a 3 ohm resistor. Let's find the current through it. So we know there's a 2.8 voltage drop across it. We know it's made of 3 ohms. Let's double check. Yep. Oh. Sorry, I did that backwards, didn't I? Oh no, that's right. 2.8 volts drop. Yes, 3 ohms. Perfect. That's good. So 0.93 amps flows through the 3 ohmer. Got a 4 ohmer. 2.8 volts there. And 4 ohms. 0.7 amps flows through there. Okay. I think we've solved everything, right? We've solved current here, and current here, voltage drop here, voltage drop here, voltage drop here, voltage drop here, and current here. Okay, so everything is solved. It's a little bit messy. Normally I'd get you to just organize it into a nice chart. It would look something like this. 1, 2, 3, 4, and then if I could draw a straight line, we would do voltage drop, we would do current through, right? So I has a voltage drop of 6 volts. It also has a current of 6 amps. Number 2, where is number 2? Number 2 has a voltage drop of 3.2 volts. And did we find the current in number 2? I don't think we did yet, but we can in a minute. Okay, then number 3. And 0.7 amps. And volts, 2.8 volts. Okay, so for the, need the current through the 2 ohm resistor. So it, I believe, had the 3.2 volt drop. Okay. Oh, haha. We already should have known that actually, because we called that out before, right? That was the amount left over, and there should be 1.6 in there. So our math checks out. It's good. We had already figured that out. Okay, any questions about that? Ready to try some on your own? All right, sweet. That is the end of that.